Exercise 2332 asks you to make an azo dye from the vapors of gasoline and an alkyl halide. Now, we can start this by doing a retrosynthesis. They give us the product, so we can start with that and think about what reactants, what reagents we would need in order to make this. We can think backwards. In the last exercise, the previous video, what we were doing was we recognized an azo dye from the two nitrogens double bonded with benzene rings on either side. And we knew we could make that from the two rings using a diazonium ion. But we had to figure out which ring should have the two nitrogens on it. It was the more deactivated ring. The more activated ring would act as a nucleophile to attack it. So let's go through the same procedure and think about each of these branches. Here we have a nitro group, which is a strong deactivator. That's the only branch on that ring. On the other side, we have an alkyl group. That's a weak activator. And we have an amine. Now there are two electrons here. There's a lone pair on that nitrogen. A lone pair in an allylic position that's not getting pulled away from the ring, that is the sign of a strong activator. So you could see how this ring on the right is much more activated than the ring on the left. For the ring on the right, each of these branches are pushing electron density into the ring, which makes it more reactive. There's more negative charge there, itching to attack something that's positive. On the other hand, the nitro group is pulling electron density away from the ring, and so this ring is not going to function well as a nucleophile. It's the more deactivated ring that gets the diazonium ion on it. The other ring is going to act as a nucleophile. So we could have the diazonium ion here, and just in terms of the mechanism, this would act as a nucleophile, attack this, and push the pi electrons there. That would give us our diazonium, or our azo dye. Okay, so if we had these two pieces, we could make our azo dye. But how can we make these two pieces? We have to work backwards until we have just benzene and isopropyl chloride. Okay. So let's try working backwards with each of these to benzene. And because we're working backwards, I'm going to use retrosynthetic arrows. So that's those two arrows with the one head. This means I could make this if I had these things. Okay, so how could I could make this diazonium ion if I had a primary amine. That's how we know how to make diazonium ions. Now we'll worry about the specific recipes in a second. I just want to sort of work backwards and see where we'll get. So we know that if we have a primary amine, we can make a diazonium ion out of it. Now this primary amine has two groups on it. It has a nitro group and it has an amine. We've already seen that, and actually, let me bring that table back that I was using just a second ago. You'll notice that these two branches are para to each other, right? If you start counting at one of the nitrogens, you get 1, 2, 3, 4. If two branches are 1, 4 on a benzene ring, that means they're para. So you want to add these in the para orientation. So let's think about what type of directors they are. The nitro group is a strong deactivator and a meta director. So we don't want to add that one first. We don't want that to be on the ring first. The other group, the amine, has a lone pair on the benzylic position. That's a strong activator. So if we work backwards, we can make that molecule from this one, because this is an orthopara director. It's a strong activator and therefore an orthopara director, and we want this on the para position. We wouldn't be able to make this from the other alternative. We wouldn't be able to make this from this because this is a meta director. And so the NH2 would add meta if we tried to make it that way. So that would not work. We have to start with this. Now we're working back until we get benzene. How can we make this from benzene? We've seen this before in this chapter. You can make NH2 from NO2. And you can make NO2, you can add that onto the ring from just pure benzene. Okay, so that's a sort of plan working backwards. We'll have to think of all the recipes for these things, but that at least explains how to make this piece that we need, the diazonium ion that we need to make this dye. If we have benzene, we can put a nitro group on it by doing nitration, and then we can reduce that in order to get this amine. Then we can add a second nitro group, para. Then we can turn the amine into a diazonium ion and do our reaction to get the Azo dye. Okay, so that took care of one of the rings. Now let's think about this other ring. How can we make this? Well, we've seen how we can make this amine from a nitro group, right? If you have a nitro group, you can make an amine. So we could make that if we had an NO2 there. And we could add an NO2 there. Now, here we have to think about the directing effects. We have two branches. Which one do we want to add second? Which one do we already want to be there when we add the second one? And if you count these, you'll notice these branches are 1, 2 to each other. If two branches are 1, 2 on a benzene ring, they're called ortho. So we want these branches to add ortho. Well, the isopropyl group is an alkyl group. It's a weak activator and an ortho-para director. So this is an ortho-para director. The nitro group we've already seen is a strong deactivator and a meta director. So we could make this, we could have these two add on the ortho position if the ortho-para director is there first. If that's there first, then we can add this nitro group on the ortho and para positions, because this is an ortho-para director. And we could make this, we could add that onto benzene, just pure benzene, by doing a Friedel-Crafts reaction. So this is a sort of outline for making that molecule on the right that we needed in order to make our Azo dye. Okay, well, the time has come. The moment of truth. We have to turn all these retrosynthetic arrows around and figure out the actual recipes. Remember, the actual recipes in order to create each of these changes. Okay, let's go in the same order we did before. Let's start over here on the left. If we're starting with benzene and we want to add a nitro group on it, all we have to do is do a nitration. That's HNO3 and H2SO4. This is one of those aromatic substitution reactions that we reviewed in the video on the reactions of aryl diazonium salts. So that puts the nitro group on there. Now we can turn a nitro group into an amine by doing a reduction. Change bonds to oxygen, an electronegative element, with bonds to hydrogen. The reduction that we use here, there's a specific recipe for this. It's iron or zinc in HCl. Again, this is one of those reactions that we saw in a previous chapter and that we brought back in that previous video on the reactions of aryl diazonium ions. Now, once we have that ortho-para director there, we can we are tempted, we are very tempted to do another nitration, HNO3 and H2SO4, but there's a problem. This normally does add an NO2 onto the molecule, and because this is an ortho-para director, we would normally get it on the ortho and para positions, especially on the para position because this is pretty bulky. The problem is this amine is a base, and these are acids, so they'll interfere with each other. This will do an acid-base neutralization reaction instead of the nitration. This will just steal all the hydrogens for itself, and you won't get the mechanism that we drew for that on a previous test. Then you won't end up getting the nitro group added. So what we have to do is we have to neutralize the lone pair there. We have to make it more stable. And we've seen this, a way to do this, in a previous exercise in this chapter, in one of the videos on the reactions of aryl diazonium ions. We can acetylate it. And we've talked about how the biology does this too. In biochemistry, you often add an acetyl group. That is 2 carbons with a double bond to an oxygen. You often add that group. Now here we're going to add it by using an acid chloride. You often add that group to start and stop your body from replicating DNA at certain places. So it's biologically a very interesting reaction, acetylating something. Here, if we treat this this will act as our nucleophile. This is our leaving group. We do a nucleophilic acyl substitution. What that would give us would be that molecule there. Notice that the nitrogen added to this group and replaced the chlorine. Then you can do the nitration. Then you can add HNO3 and H2SO4 because this lone pair is not as basic anymore. It's allylic to this carbonyl. And so it's being spread out and stabilized through resonance, so it's not going to act as a base anymore, and these acids can do their nitration. So you would end up with you'd end up with the NO2 there. That shouldn't have been there here. Sorry about that mistake. So you'd have this here, you'd do this acetylation, and you'd end up with this. You wouldn't have that NO2 there yet. You'd add the NO2 after this is acetylated, after this lone pair stops being quite so basic because it's being stabilized through resonance. You can add the nitro group by doing a nitration. And then you just take the acetyl group off by doing an acid catalyzed hydrolysis. So if you add acid, you hydrolyze this amide. That's how amino acids come apart, and you drew the mechanism for that on a previous test. Now that would give you this structure here. Okay. Once you have that structure, you have your amine with the nitro group on it. You can turn the amine, the primary amine, into a diazonium ion by adding NaNO2 and HCl, that classic recipe there. So that gives us a sort of pathway for making this molecule on the left. We first put the nitro group on, then we reduce the nitro group to an NH2. We have to protect the NH2 so it doesn't do an acid-base reaction, and then we can do the nitration. Once we have the nitration, we can take the acetyl group off, and then we can turn the primary amine into a diazonium ion using sodium nitrite and HCl. Okay, so much for that reaction. Now let's think about this other pathway. Let's reverse these arrows. Think about the specific reactions that we'd use here. If you wanted to put an isopropyl group on benzene, you could just do a Friedel-Crafts alkylation. And we were allowed to use isopropyl chloride. That was one of the reactions. They said we can use benzene and isopropyl chloride. So here's an isopropyl group with a chlorine on it, and that's isopropyl chloride. So we can use that, and we just need a catalyst, AlCl3. We don't have to worry about this rearranging because the carbocation that could form here would be secondary, so it wouldn't rearrange to either of the primary positions. And that would add that group onto that ring. Now, at this point, we'd want to add, going to this next step, it would be tempting again to add the nitric acid and the sulfuric acid to add this nitro group. The problem is the isopropyl group is pretty bulky, and the nitro group is also really bulky, and pretty bulky. And so most of the nitro groups would go in the para position where it's not as crowded, rather than the ortho position where we want it. So before we do that, we can persuade the nitro group to add to the ortho position by doing a sulfonation. This is a sort of clever step. You can add an SO3H group as a blocking group. So if you remember, if you add fuming H2SO4, that's sulfuric acid that has sulfur trioxide bubbles coming through it, then you would add, what that does is that would add an SO3H group. It's sulfonation. And if you look at the reactions that we listed in that previous video that reviewed the aromatic substitution reactions, this was in it. This was in that table. So here, let me just quickly refer back to that, just so you can see. So here, in this table, this review of aromatic substitution reactions, you can see that if you have fuming H2SO4, it puts the SO3H on it. Now that's a really bulky group, SO3H. Very bulky. And so, sorry about this, all this movement. So it's a really bulky group. So now this is blocking the para position. And we can add the nitro group. The nitro group has no choice. Now, if you remember, this is a moderate deactivator. And it's always the most activating group that determines the directing effects. So here we have two branches. One is a moderate deactivator, the other is a weak activator. The more activating group determines the directing effects. So this is an ortho-para director, and so any other branch we add onto this will add ortho-para to that branch. So if we do the nitration now, and we add nitric acid and sulfuric acid, the nitro group will have no choice. The para position is not open for business. It has to add on the ortho position. And then we can get rid of this by just adding water. So it was concentrated, fuming H2SO4. If we just add water, dilute H2SO4, then it reverses the reaction. If you remember the mechanism for sulfonation, which we walked through in a previous chapter, if you remember, every step was reversible. And so you can put it on by making it more concentrated. One of the products was water, and so you can take it off, reverse the reaction by adding a product that shifts equilibrium to the left toward the reactants, using Le Chatelier's principle. So we did a sort of clever thing here, because otherwise our yields would be very, very low. If you just added nitric acid and did the nitration, most of it would add onto the para position. So to prevent that from happening, we added a separate bulky group, a sulfonation group, as a blocking group. It blocks the para position. And then we did the nitration. The nitro group had to add to the para position, and finally we took off the sulfonation product by adding water, reversing the equilibrium through Le Chatelier's principle. So that gave us this product. Now, we can turn the nitro group into an amine by doing a reduction. And here that was with iron or zinc and HCl. Well, at that point, we have these two things. We can combine those, and together, once you have those two, they would make your Azo Dye. And so you can see in this really kind of breathtakingly beautiful synthesis, you could see how starting with the vapors of gasoline and this alkyl halide, you could make an Azo Dye that truly brings color to your life.